Welcome to the second part of my talk. So, in the first part, I kind of roughly explained what are universal circle actions and how do you lift universal circle actions to show three manifold groups are left orderable. So, in this part of the talk, I will just present some result obtained by applying those two circle actions I talked about in the first part. Let's first look at cyclic branch covers. For simplicity, I will just assume K is a prime knot in S3. So the n-fold cyclic branch covers, denoted by sigma n of K, are irreducible. So conjecturally, for any given knot, there should be this integer n knot between 2 and infinity, such that pi 1 of the cyclic branch cover is left orderable as long as n is greater than or equal to n naught. So particularly, if n naught is equal to infinity, that means none of the cyclic branch cover has left orderable fundamental group. If n naught is equals to 2, that means every cyclic branch cover has left orderable fundamental group. Okay. And by the way, there is the same picture should hold for CTF and NLS as well, according to the L space conjecture. I'm just not mentioning those two in this part of the talk, but you should always ask yourself, is the same thing true for the other two as well? Okay. So in fact, you can actually find example of n not equal to infinity and n not equal to, I guess, n not strictly bigger than 2 within the collection of two bridge knots. So I list some reference right down there. You can go check it out. In the later part of the talk, I'm actually going to give you result where a knot is equals to 2. Okay, so that means all the cyclic branch covers have left orderable fundamental groups. So for simplicity, I would just restrict myself to L space knot. So a knot is called L space knot if there exists a finite slope so that xp over q is an L space. There are some properties of L space knot which will be crucial for us. First, we know if K is L space knot, then it's fibered. Moreover, the monodromy of the complement of the knot is actually right veering. So a right veering mapping class just means, see if I can draw this for you. So if this is your fiber, and then your monodromy is H, right veering just means if you're looking at any arc starting at the boundary of the fiber, you look at the image of this arc under the monodromy, that image will be on the right side, roughly speaking, on the right side of the original arc. Okay, so if your mapping class satisfies this property, then it's called right veering. This is actually a very important concept if you are considering the context structure supported by the open book given by F and H. That's kind of tell you something about the tightness of the context structure. Okay. So that's one property we would need from L space knot. Another thing is if K is a satellite L space knot, then it turns out the patterns of K is a closed braid in the solid torus. Okay. So later on, when I state the result, I will tell you which properties of the L space knot are used. So basically, given any knot, as long as it satisfies those properties, the same statement should hold for those knots as well. Okay. So let's first just look at torus knot. Basically, everything is understood for torus knot. This is done by Gordon and Littman. Essentially, if the torus knot is not those 2Q torus knot 3, 4, 3, 5, then all the cyclic branch cover will have left-orderable fundamental groups and admits CTF, so it's not L space. And if your torus knot is one of those things, then they will tell you precisely when you will have left-orderable fundamental group and CTF as well. So next, let's move to hyperbolic knot. So the theorem is if K is a hyperbolic L space knot, then pi 1 of the cyclic branch cover is left-orderable for any n bigger than or equals to 2. And the proof of the theorem is essentially using the fact K is fibered. Okay, we need K is fibered and hyperbolic, and we also want the malodromy is right veering. So if you have any hyperbolic fiber knot with right veering malodromy, it's the same thing is true. The proof is using the universal circle action from pseudo-Nassau flow, and I will just roughly explain this. First, you are going to have a pseudo-Nassau flow on the complement of the knot. This is essentially given by suspension of the malodromy because it's hyperbolic. Okay. And then you are going to pull back this pseudo-Nassau flow on the cyclic cover. This is a cover of the knot complement. To get the cyclic branch cover, you just need to, do a Dunn-filling, do a meridian Dunn-filling along the cyclic cover. It turns out it's actually very easy to extend a pseudo-Nassau flow to the Dunn-filling manifold. If you know something called degeneracy locus, that just basically tells you if you Dunn-filling slope intersects the degeneracy locus at least twice, then you can extend the flow to the Dunn-filling manifold. So here you get a pseudo-Nassau flow on the cyclic branch covers. Then you want to show the action actually lifts, and in this case, it does lift. Okay. So that's for hyperbolic knot. You can also do something when the hyperbolic knot is not fibered, but I'm not going to talk about that. I do want to move to satellite knots. So again, if you have a satellite L space knot, then all the cyclic branch cover will have left-orderable fundamental groups. And in this case, we are using the universal circle action coming from CTF. The key properties we need from L space satellite knot are companion knot is fibered and the pattern is a closed braid. Okay. And so here we are first going to construct CTF on the cyclic branch covers. The construction is essentially, you are going to use the fact the cyclic branch cover of the satellite knot is going to be a union of cyclic branch cover of the pattern in the solid torus, and then union a couple of copies of not branched, but covers, cyclic covers of the complement. This is for X is the companion knot. Okay, and then when you construct CTF, you want to have CTF on each piece in this union and then piece them together. There are some cases it's more difficult than the other. particularly when the pattern is 2Q torus knot. So, in that case, this piece just becomes a thickened torus, so that will cause a little bit of trouble. But that's a general idea. And then to show the universal circle action actually lift, we want to show the order class of the tangent plane bundle of the foliation is equal to 0. And here it is equal to 0, essentially because the order class is actually invariant under the cyclic action of the cyclic branch cover. Okay. So that's basically the two results I want to show you. One is using pseudo-NASA flow, another one is using CTF. And by the way, for satellite knot, Gordon and Lehman had this conjecture. It's basically said give any prime satellite knot, all the cyclic branch covers should be CTF, LO, and NLS. Okay, so this is not just a hold for an L space knot. Conjecturally, this should hold for any prime satellite knot. So this is a conjecture, okay, by Gordon and Lehman. So in the last of the talk, I will just roughly, very quickly tell you what happened when you're trying to use the same strategy to done fillings. And again, for simplicity, I will just restrict myself to K in S3 and the G is the genius of the knot. It is known that X PQ is not an L space for any PQ in interval I, where I is either the whole interval, that means your knot is not L space knot, or it's from negative infinity to 2G minus 1, plus or minus if your knot is actually an L space knot. And a similar type of result also established for large class of knots in terms of CTF. And here, let me just give you some example. In the work by Delman and Roberts, they showed if K is an alternating knot or non-L space Montesinus knot, then for any done filling, you are going to have CTF. Okay, so none of those knots are L space knot. Then for L space knot, CD Krishna showed if you have K is positive closed 3 Brit, then she actually managed to construct CTF for slopes from negative infinity to 2G minus 1, which again match the picture for NLS as well. And then finally, I will just mention if you look at some early work of Rachel Roberts and she look at just the fiber knots in general, then basically she tells you you are going to have CTF for slopes I for I is equal to either the whole interval or from negative 1 to positive infinity, depending on, again, the monodromy of the fiber knots. But just to summarize, this just tells you for NLS and CTF, you do get this type of large intervals. And according to L space conjecture, the same thing should hold for interval of LO slopes. And since we have all of those very nice CTF, it's very natural to wondering what happened to the universal circle actions coming from those CTFs that do the circle action lift. And then unfortunately, what happened is if you have any CTF on a done filling xp over q such that leaves of the foliation actually transfers to the core of the done filling solid torus. So this condition actually is satisfied for all of the co-orientable top foliation I mentioned above. Then if you look at the set of slopes for which the universal circle action lifts, it turns out that this set, first of all, is nowhere dense. Okay, that means you cannot get an interval of slopes coming from lifting universal circle action. Then moreover, the set when g is bigger than 1, this set of slopes is also bounded between plus or minus 2g. And what happened when g equals to 1 is you do get arbitrary large slope, but those slopes are only integer slopes. Okay. So so that just tells you again, it's not very effective if you use the universal circle action to show left-orderability of done fillings of the manifold. Okay. So I think I will just stop here. Thanks for your attention, and I hope you enjoyed it.